Hi, gents. What we're looking at here on the screen is a portion of the AP Physics 1 equation sheet, and you can see it in the highlighted pieces there. We have all of these equations we've been talking about recently. Period is equal to the inverse of a frequency. Period of a simple harmonic motion is 2 pi m over k. Simple period of a simple pendulum is approximately equal to 2 pi L over g, as long as the angles are small. And the position of the mass in simple harmonic motion is equal to the amplitude times sine or cosine. It doesn't really matter which. It just depends on where you start your motion, either at its maximum displacement or its zero displacement. That will determine if it's sine or cosine. And the cosine of 2 pi frequency times t. What I wanted to do is I wanted to go through and I wanted to derive for us not just the position equation that we did experimentally. I also wanted us to take a look at the velocity and the acceleration equation. So this document right here is going to be walking us through a derivation of velocity and acceleration equations. So we can recognize here, again, doesn't matter if it's sine or cosine, as long as it's sinusoidal. We have the position of simple harmonic motion at any time t in terms of amplitude and period, and in terms of amplitude and frequency. So some of the things to kind of keep in mind is in that equation, x is the position of the mass at any time t. We're making the assumption, since we're using sine, that at time 0, our position will be 0, and that is at the equilibrium position. Since we know that sine of 0, so when time is 0, sine of 0 is 0, so therefore our x position would be equal to 0 too. This would be 0 at time 0. Therefore, we're using sine to model it. If the equation, if the equal position is the 0 position, these equations can work also for horizontal or vertical springs. It doesn't really matter. Okay. The amplitude of oscillation in those equations is for a horizontal spring on a frictionless surface. The amplitude would also be the x, or the stretch of the spring. The t in these equations are the period. Script f in the equations are frequency, and t is the time for which you would like to know what the position x is. So just kind of a recap of what those variables mean in those equations. So on to the new stuff. One of the things that is new for us that we haven't talked about yet or seen in any video is those position equations above can also be used for a simple pendulum to a very good approximation, as long as you kind of limit the conditions that you're allowing. So again, like with the period equation, keep the angle less than 15 degrees. And if you look down here, if we have this mass oscillating back and forth, the actual motion of the pendulum is going to be on these red arc lengths. When it swings over here, it's positive x. When it swings over there, it's negative x. If we keep the angle small, then this arc length, red positive s, is going to be very close to this linear length, this horizontal distance here of x max. So when we swing all the way out here to the highest location, will also be horizontally over at x max. As the mass swings over the other way, we'll be over at this horizontal location, negative x max. So as long as these angles theta are small, this arc length negative s and this length negative x max, they're really close to each other. As it swings over this way, this positive arc length s and this length positive x max are really close to each other. So we can use those equations above to find the horizontal position for a very good approximation. It won't be perfect, but as long as the angles are small, it's going to be really darn close. So that's kind of a new thing. So one of the things I want to do is I want to use those equations above to derive velocity and acceleration, and we're gonna use calculus ideas, but we're going to back those ideas up with some of the graphing stuff that we know. So don't let it freak you out if you don't know calculus or if you don't recognize all of it. It's going to be useful perhaps someday in the future for you, but I'll back it up using what we know about graphing. So using the definitions of acceleration, the calculus definition of acceleration velocity, Velocity, by definition, is the first derivative of position with respect to
time. You notice the little d's. If you replace those with deltas, that equation looks very similar to the one you know. Acceleration
in the calculus definition is acceleration is the first derivative of velocity with respect to time. Change that little d to a delta, and that equation looks very familiar. Now this, I don't know how many of you recognize this or not, but this is essentially saying that acceleration is the second derivative of position with respect to time. And again, if any of that is completely unknown, or if any of that is just sort of known, no problem. We're going to back it up with graphing. So using those calculus definitions, if we take the derivative of a sine 2 pi over period times t, if we take the derivative of that with respect to this variable t, what we end up with is, from the sine function, we get a cosine function. So you can see the familiar amplitude here, 2 pi over period times t, all of that's familiar. I won't go into why, but this 2 pi over t will come out from inside here when we take the derivative. And so we have a velocity equation here in terms of period, and the same velocity equation in terms of frequency. Now, to back that up using what we know about graphing, we know that velocity is the slope of a position time graph. So here is a position time graph. Here is a position time graph, and what I've put on there is some slopes. So I have the slope at position A, which is right here. I have the slope at position B, position C, position D, and position E. So I have a positive slope. All this stuff over here is basically saying the same thing. We have a positive slope at A, a zero slope at B, a large negative slope at C, a zero slope at D, and a large positive slope at E. So if we take those slopes, aka the velocities, at different times, and we plot them on a velocity time graph, we get large positive at A, zero velocity at B, large negative at C, zero at D, large positive at E. And we also can see here that as the slope goes from, as the position goes from point A to point B, the slope is going to gradually change from large positive to zero. So the velocity is going to change from large positive to zero. As the position goes from B to C, our slope is going to change from zero to big negative. So from B to C, our velocity will change from zero, to big negative. And then we'll have a gradual change in slope from C to D that goes from big negative to zero. You can see the value of velocity goes from big negative to zero. And then finally, from here to here, we go from a zero slope to a large positive slope. So our velocity value should go from 0 up to big positive. And those changes are going to be gradual. So the green curve here is showing those gradual changes in velocity. And lo and behold, what shape is that? But it's a cosine. So that kind of matches with what the calculus is saying. Our graphing knowledge matches that. So since we know those velocity equations have cosine in them here, we have a cosine and a cosine, we know that the biggest values that cosine can be is a 1 or negative 1. And so we can use that to find out what the equation for the maximum velocity would be. So let's go back up here. If this right here, if the biggest that this can be is 1 or negative 1, that must mean that the biggest the velocity is going to get is either positive 2 pi over period times amplitude, or negative 2 pi period over amplitude. Or in terms of frequency, it would be 2 pi frequency times amplitude. So this would be velocity max. Now we also know for simple harmonic motion, we know the period is equal to 2 pi times the square root of m over k. So if I take the period and substitute it in right here, Vmax can also be stated like this. Here's my 2 pi, which is right here. Here is my t, which is equal to 2 pi square root m over k. Here is my amplitude here. It's right there. Notice the 2 pi's are going to cancel. These guys are going to flip over because it's on the denominator, and we end up with maximum velocity is equal to amplitude times the square root k over m, which if you look on page 301 in your book, boom, you'd see that equation there.